The first discovery on the list is that the universe had a beginning. And by the universe, I mean the space-time fabric itself and matter and energy within the universe. Two books have come out recently at nearly the same time that summarize several of the discoveries on our list, including this first topic. One is by Steve Meyer at the Discovery Institute in the US, and another is by two authors in France. The discoveries were made many decades ago, and many books have been written about them, but these two are very good recent summaries. To begin, I'll go over some important observations. First is that light and other forms of radiation are detected that originated from sources which are now very large distances away, meaning billions of light years, and are moving away from us. The images in this slide are from the Hubble and James Webb Space Telescopes. Each field of view is about that of a grain of sand held at an arm's length. Each point of light is a galaxy. The James Webb image identifies more objects and provides more information about each object. The second important observation is that the wavelengths of the radiation from each galaxy are shifted toward the red side of the spectrum by a factor roughly proportional to the distance of the galaxy from us. This slide shows an image of the velocity versus distance diagram that Hubble and his colleague published in 1931. This was very convincing evidence, probably the first really persuasive evidence that the universe is expanding. The slope of that line is called the Hubble constant. The red shifts occur in whatever direction we look and imply that the fabric of space itself is expanding. A helpful analogy is that of a balloon with small coins attached to represent the galaxies. As the balloon expands, the coins move away from each other, and the further the initial distance of separation, the faster they move away from each other. That's the Hubble law. Now imagine a sine wave painted on the balloon. As the balloon expands, the sine wave will be stretched. The redshift data therefore imply that the fabric of space itself is expanding. A lot of research effort has gone into measuring the velocity versus distance relationship. This plot shows the data since 1922. The red box near the origin is the initial data from 1922. You can see that the linear relationship holds over very large distances. This plot shows how the value of the Hubble constant, the slope of the line, determined experimentally, has been refined over time. Prior to the observations of Hubble, there was a very important theoretical development. Alexander Friedmann, in 1922, solved Einstein's equations of general relativity and showed that the universe could not, in fact, be static. Prior to that, many people believed that the universe was static and that the universe did not have a beginning but always was. Einstein had this view and had introduced an extra factor called the cosmological constant into his equations to make them consistent with the static universe. He initially rejected the conclusion of Friedmann, assuming it to be an error. He published this statement in the same journal that published Friedmann's work. The results concerning the non-stationary universe contained in Friedmann's work appear to me suspicious. In reality, it turns out that the proposed solution given in it does not satisfy the field equations. However, after a meeting with a friend and supporter of Friedman, Yuri Krutkov, where they went over the calculations step by step, Einstein realized that he had made the mistake. He then published this in the same physics journal. As Mr. Krutkov convinced me, and thanks to a letter from Mr. Friedman, my objection was based on a miscalculation. I now consider Mr. Friedman's results to be correct. These provide a new insight. The combination of Friedman's calculation and the observations of Hubble were persuasive evidence that the universe was not static, and strongly implied that the universe had a beginning. This was shocking to many scientists at the time, and continues to be shocking to many even up to the present. This slide lists some quotes from well-known scientists. Arthur Eddington, an English astronomer and physicist, said this: "Philosophically, the notion of a beginning of the present order of nature is repugnant to me." Robert Jastrow, in his book God and the Astronomers, said it's distasteful to the scientific mind. In the same book, he quotes Philip Morrison as saying that he would like to reject it. And Stephen Hawking, in his book A Brief History of Time, said that many people do not like the idea that time had a beginning, probably because it smacks of divine intervention. This is interesting because scientists are supposed to be dispassionate and are not supposed to prefer one result over another, but rather should be unbiased in their search for the truth. But of course, scientists are human just like everyone else, and they do have biases. Friedman lived and worked in St. Petersburg. He published his result in 1922, which was shortly after the Bolshevik Revolution, and the Marxist-Leninist ideology of dialectical materialism had taken hold. The claim that the universe had a beginning, and the obvious implication that there was a creator, was branded as anti-Soviet propaganda, and those promoting this idea were declared enemies of the Bolshevik state. In the book Dieu, la science, les preuves, or God, Science, and Evidence, the authors recount that Friedman, many of his students, and many other scientists were persecuted and some assassinated because of their work showing an origin of the universe. This persecution continued through the regime of Stalin, and such persecution also occurred in Nazi Germany. This slide shows a page from that book with photos of some of the scientists and scholars who were persecuted. Another very important calculation was made in 1948. In that year, Robert Herman and Ralph Alpher predicted that a radiation should be left over from the initial creation event. And that comes from the fact that if the universe started in a very hot, dense state, as is implied by Friedman's calculation and Hubble's observations, then electrons and protons would be dissociated early on. But as the universe expanded and cooled, at some point, electrons and protons would combine. And when that happened, a radiation would be released. They predicted the temperature and the wavelength distribution of that radiation. And this slide shows that based on an estimate of the temperature where that would occur and the expansion factor, since that time, they predicted that the radiation should have a temperature of about 5 degrees Kelvin. The person in the center of this image is George Gamow, who was the PhD advisor of Ralph Alpher. Many years earlier, George Gamow had been a student of Alexander Friedman in Russia, and he was among those persecuted for promoting a beginning to the universe. But Gamma was able to escape the Soviet regime when he was granted a visa requested by Niels Bohr and Paul Langevin to attend a scientific conference. The cosmic background radiation predicted by Hermann and Alpher was discovered by accident in 1965 by Arno Penzias and Robert Wilson working at Bell Laboratories. They were working with a sensitive antenna for radio waves and observed a low signal present in all directions that appeared as noise but was 100 times stronger than expected. After consulting with other researchers, they realized that the temperature of this signal was in the range expected for the cosmic microwave background, and they published the result alongside a theoretical paper by another group. They received the Nobel Prize in Physics in 1978 for this discovery. The cosmic microwave background radiation is nearly uniform in all directions. It doesn't come from a single source, but rather it's present everywhere in the universe. It's believed to represent radiation with a redshift of about 1,100. It's the earliest phenomenon that we will ever observe. This plot shows the wavelength distribution of the radiation compared with the predicted distribution. You can see that it's an exact match. The discovery of this radiation with exactly the predicted characteristics convinced the scientific community that the universe indeed began in a very hot, dense state. This theory came to be known as the Big Bang, which was originally a term of derision coined by Fred Hoyle, who along with others had proposed a steady state theory that would avoid the existence of a beginning to the universe. However, the discovery of the cosmic microwave background radiation ended the debate in favor of the Big Bang. A final important observation was the discovery that tiny fluctuations exist in the cosmic microwave background radiation. This was discovered by a team led by George Smoot in 1992. These fluctuations have since been studied in great detail by several experimental probes, since the characteristics are believed to provide important information about the state of the very early universe. This slide shows a diagram depicting the development of the universe following the period during which that burst of radiation occurred. The cosmic microwave background radiation is believed to be the earliest phenomenon that will ever be observed. This slide cites two important theoretical developments. The first was the publication of singularity theorems by Hawking, Penrose, and Ellis. These showed that if general relativity is adopted as the theory of gravity, singularities exist in both space and time. And then it follows that a singularity in matter and energy also exists at the beginning. This means that there was a beginning and that no physical reasoning can be applied beyond or before that point. However, these theorems depend on general relativity, and it's unlikely that general relativity is an accurate theory of gravity at very small scales. For a radius of curvature estimated by Hawking and Ellis below the range of 10 to the minus 12 to 10 to the minus 33 centimeters. And so physicists have searched for a quantum theory of gravity that could be applied at even smaller scales. But in 2003, Bohr, de Guth, and Vilenkin published a generalized proof for a beginning to space, time, matter, and energy for any expanding universe. This is a generalized theorem in that the only assumption is that the universe is on average expanding. Following this, the publication of this theorem, one of the authors made this statement: with the proof now in place, cosmologists can no longer hide behind the possibility of a past eternal universe. There is no escape. They have to face the problem of a cosmic beginning. Now, there's no such thing in science as an infinite search, but these theorems provide very strong support for the notion that the universe, meaning space, time, matter, and energy, had a beginning. For more details of these theorems, I refer you to Steve Meyer's book and the references cited therein. This is a diagram highlighting ideas of what may have occurred prior to the period of the release of the background radiation, indicated by the arrow. These periods are not directly observable. Models of these earlier events are based on the standard model of particle physics, which has been established from experiments involving particle accelerators. Models of these earlier events must be consistent with the data that we can actually observe, such as the cosmic microwave background and the distribution of light elements in the universe. The nuclei of the light elements are believed to have been synthesized at a time substantially earlier than the release of the background radiation. Notice that the theorems of Hawking, Penrose, and Ellis, based on general relativity, apply for the entire history unless there was actually a period where the entire universe had a radius of curvature less than 10 to the minus 12 centimeters. This slide shows a quote from physicist Paul Davies, who said this following the publication of the space-time singularities. He said, if we extrapolate this prediction to its extreme, we reach a point where all distances in the universe have shrunk to zero. We cannot continue physical reasoning or even the concept of space-time through such an extremity. On this view, the Big Bang represents the creation event, the creation not only of all the matter and energy in the universe, but also of space-time itself. Now I want to emphasize a point that will recur over and over again in these presentations. The point is that the discovery itself is not controversial, but the conclusions drawn from the discovery differ among various experts. I'll start with Alan Sandage. And this story is told in detail by Steve Meyer in his book. Steve Meyer was in the audience when Alan Sandage made the statement that's described on this slide. Sandage was an agnostic with a materialist view of science, but became convinced that there's a mind behind the universe based on this evidence, based on this discovery. He said this: here is evidence of what can only be described as a supernatural event. There's no way this could have been predicted within the realm of physics as we know it. I now have to go from a stance as a complete materialistic rational scientist and say this supernatural event to me gives at least some credence to my belief that there is some design put in the universe. Another scientist, Robert Jastrow, describes his response to this discovery in this quote. He says in his book, "For the scientist who has lived by his faith in the power of reason, the story ends like a bad dream. He has scaled the mountains of ignorance. He is about to conquer the highest peak. As he pulls himself over the final rock, he's greeted by a band of theologians who have been sitting there for centuries." But in a subsequent video interview, he stated, but I can't accept it. And he went on to say that he's a materialist in his philosophy and will maintain that materialism despite the evidence. So this is an important point. The amount of evidence that leads one to conclude that materialism isn't a complete description, that there is a mind behind the universe or a cause outside of the physical universe, that's a personal decision. And that for some people, no amount of evidence would ever be enough. So to summarize, the first discovery is that the universe, meaning space, time, matter, and energy, had a beginning. So what do you think? Does the origin of the universe from nothing constitute an informational discontinuity?